Welcome everyone. My name is Leni Wallenberg and I lead the CCAF's program on low emissions development. CCAF's is the Climate Change, Agriculture and Food Security Research Program of the CGIAR, and together with the GRA we are co-hosting the CLIFF-GRADS program and this wonderful webinar series. So it's really my pleasure today to be able to introduce John Porter. But before I do that, just a few quick points about logistics that I think most of you are familiar with. This is a webinar, and so there's no audio and video of the participants, but you can use the chat. And then in particular, we're going to encourage you to use the question and answer function. And I would encourage you to also place your questions during the call. Don't wait until the end, because it's wonderful to have a lineup of 10 or 20 questions by the time the speaker is done. This is the 8th of 12 of the series, and we're really excited that that we've gotten this far. So I've heard that things have gone very, very, very well. So John Porter, it's hard to describe John because he has so many accolades and has contributed so much to the field. He is at heart, if I can venture to say so, an expert in everything from climate change to agroecology to biological modeling, and really has looked at this intersection, especially of climate and agriculture. He's published more than 140 papers in reviewed journals, won no less than 4 international prizes, has served as the president of the European Society for Agronomy and the chief editor of the journal. He led the writing of the chapter on food production and security for the IPCC's 5th assessment. He, as you can see, has a number of university affiliations on the slide here, and he was elected as both a fellow of the Royal Swedish Academy. He is Danish, mind you, as I understand it, John? Yeah. But elected as a fellow of the Royal Swedish Academy for Agriculture and Forestry and the European Academy of Sciences, and no less was knighted by the French government. So Hazel, I don't know why you have 2 knights in your series, but it's very impressive. I think other than that, I'll just mention that John is reportedly retired, but then just mentioned that he was appointed to be chief editor of one of the Frontier journal series. So you can see that he's as active as ever. And he is also a recent, I guess, repeat grandfather. So congratulations as well on that news. So okay. over to you, John.
Well, thank you very much indeed. It's a great honor for me to be involved in this program, and thank you very much to Hazel and everybody for the invitation. Hazel and I met actually for the first time in San Antonio last year at the ASA meeting in San Antonio, and I'm really pleased to be involved in this. This is part of something that I've been working on since I retired and have been based part of the time in Montpellier, because in Montpellier we have this One Planet Fellowship program, which was basically set up by Gates and the President of France. This is to make or to facilitate exchange between climate change postdocs in Africa and climate change postdocs in Europe. And so this, what we're talking about today, is just fitting in very nicely with that work we've been doing in Montpellier. So yes, today I'm actually going to try and cover 2 issues. One is some work about how you can try and estimate the greenhouse gas emissions from agricultural systems. Some work I did with Pete Smith and a PhD student here in Copenhagen. And the other, and as they say in Monty Python, something for completely different. I thought it's important really for PhD students and young scientists to have at least thought about what are the norms of science, and in this enterprise that we're engaged with, what are the norms, what are the behaviors of science, what is science trying to do, and how can we perhaps look at science and how it can be used. So those are 2 rather distinct themes that I'm going to talk about for the next 45 minutes or so. So I have to go down to the next slide. Yes, there we go. This is a bit of an introduction, and this is the Sustainable Development Goals, the 17 Sustainable Development Goals. And what I think is interesting about the Sustainable Development Goals is that 1, 2, 3, 4, 5, 6, 7, 8, 9 of them, with the red stars on, have something to do with agriculture and the food system. I mean, zero hunger, good health and well-being, responsible consumption and production. These are all revolving around the stuff that we do. That you know, we've been working on, what Linny's working on, and Ngoni Chirinda's working on, and I've spent some time working on it as well. So what the point is really here, that agriculture and food systems are absolutely central to the Sustainable Development Goals. I just wanted to start off by thinking about food systems, really. I know we hear a lot about agriculture and production systems, and when we did the IPCC chapter in fifth assessment report, we did try and move away from just looking at production systems to looking at food systems, which encompass more than production, but of course encompass processing of food and consumption of food. And about 6 or 7 years ago, we did a study here of 3 capital regions, the food systems of 3 capital regions. One of them was the Australian capital region, the other one was the Copenhagen capital region, and the third one was the Tokyo capital region. This is because we were working together with Australian National University and Tokyo University in this project. And what's interesting about this is you can see at the bottom of the slide the number of people per hectare. So they almost scale by factors of 10, from 0.1 person per hectare in Australia to 4 in Denmark to 12.8 in Tokyo. So they give you an idea about how these systems can scale. And so what we did, we looked at a number of different parameters, but one of the parameters that we did look at was the production and export of wheat, and how do these 3 different systems, those 3 different capitals, how do the populations of those capitals, how do they deal with the production and export of wheat? And this is the Australian capital region. You can see the production figures in that green oval shape there, and also the consumption. And this is all scaled to the populations of these different regions. And then you can have the surplus. So in fact, the Australian capital region around Canberra and the Australian capital territories is very much a surplus producer of wheat. And this can be contrasted completely with the Tokyo capital region, which is very much based on the import of wheat. And you can see that the wheat, 47% comes from the US, 23% from Canada, and 20% from Australia. Some of it is re-exported as wheat flour, but you can see that basically the Tokyo capital region, in contrast to the Australian capital region, also a little bit to the Copenhagen capital region, is very much a importer. And that difference between whether you're an exporter or whether you're an importer of food makes a difference to your greenhouse gas emissions. And this is taken from the special report, which was published in 2019, the special report that Cynthia Rosenzweig and Tim Benton and other people engaged, and other people from around the world were involved in this special report. I had a minor role in this chapter, but and what they did, and I think I was really, really pleased to see this, because they took what we tried to do in the 5th assessment to a next stage, I think, when they basically went through the literature and looked at the emissions of different components in the food system. So they looked at the emissions in CO2 equivalents of agriculture, of land use change, and things that happen beyond the farm gate. And then they were able to see how the food system as a whole, what the emissions that were involved in that actually come out as. And you can see on the right-hand side the share in mean total emissions. What I think is interesting is that if you just take agriculture, i.e. the production of food, and then the land use, the change in land for agriculture, and actually what happens to food beyond the farm gate, then it's pretty split evenly between those three different food system components. And I think this, what of course this doesn't include is what I just talked about before with the different capitals. This does not include the emissions which are to do with the trade or with moving food around the world. And I think that sometimes economists are always about, well, greenhouse gas emissions are externalities to the system. I don't believe for a minute that greenhouse gas emissions are externalities to the system. They are absolutely internalities, both into the food system, but also into the economic system we have as well. So how do we deal with this as scientists? How do we think about how we can try and get estimates of emissions? Excuse me, I'm just going to have a glass of water. When I talked about this in San Antonio, I actually had 3 possible modeling approaches, but I tried to cut it down this time to 2. And I want people who are listening to this to think about how they maybe can think a little bit outside the box about what they're trying to do when they're trying to estimate greenhouse gas emissions from food systems. And you can take a sort of spectrum really of approaches. You can see on the left-hand side of the spectrum in the blue and ultraviolet section there that you have, I mean, a lot of work has been done using very detailed simulation models to try and make estimates of greenhouse gas emissions. The whole AGMIP program has been very much involved with that. And at the other end of the spectrum, you might find less detailed, broader, using existing data, and perhaps quicker than the time consuming of running models and also validating them with experimentation. I'm not denying that that's really important. I'm just trying to give another opportunity of thinking about how we may estimate these emissions. And just to take a step back now before I go into the first modeling approach that I'm going to describe. This is a figure which is a rather old figure now. It was taken from the World Resources Institute. And this is a world greenhouse gas emissions flow chart. And you can see basically it's divided into the energy use sector, and you can see transportation, electricity and heat, other fuel combinations, industries, and how this ends up as particular end uses. And of course, the emissions of this sector are carbon dioxide, mostly carbon dioxide, almost exclusively carbon dioxide. But at the other third, if you like, the other third of the emissions are to do with land use change and agriculture, and also waste as well. And so the point is that there are 2 major categories of emissions, both the energy and economic sector and also the agriculture sector. And when people come and do the emissions, say from the energy and economic sector, they use this thing which is called the Kaya identity, which was developed by a Japanese scientist when he was working at IASA in Vienna, to look at the emissions and how you can calculate the emissions. And basically, what Dr. Kaya came up with was that you have to look at the amount of greenhouse gases per unit energy. So if you're using oil, the greenhouse gas emissions per unit energy will be higher than if you're using methane gas, for example, which has a higher thermal capacity. So the greenhouse gases per unit energy will be lower if you're using biofuels, for example, or solar or whatever. But you multiply that by the amount of energy needed to produce 1 unit of gross domestic product. And then you multiply that with how much gross domestic product there is per unit population, which is basically a measure of wealth. and you multiply that all by the population, and you can see that this allows you to calculate the greenhouse gas emissions from the energy and economic sector. And basically what has happened, the blue arrows here are trying to show you what's happened over time, is that the amount of greenhouse gases per unit energy as countries have moved more away from coal and oil to perhaps using renewable sources of energy, these greenhouse gases per unit energy have dropped somewhat. The energy needed per unit of GDP has also tended to, certainly in industrialized countries, has shown some declines. But what has not shown a decline and gone completely in the other direction is the GDP per unit population. This is basically people getting wealthier. And the population, that is also increasing as well. But what this allows you to do, what this kind of analysis allows you to do, is to break down, is to deconstruct, if you like, the factors which influence your amount of greenhouse gas emissions. But that analysis only applies for the energy use in the economic and energy sector. It doesn't do it for the agricultural sector until in about 2009, I came up with a identity equation which I thought you could be used for the land use sector. So here we have a equivalent situation to the Kaya identity. We have how much yield per unit area. We then multiply that by how much energy per unit yield, and then how much greenhouse gas emissions associated with the energy you use in agriculture, and multiply that through by the area. So this is a way in which we can perhaps taking the basis of the Kaya identity to try and simulate emissions from the agriculture sector. And when in about 2011, together with Pete Smith, who's been very involved with IPCC for many years, and a PhD student called Eskil Benison, we looked at how we could use this Kaya Porter identity to look at emissions globally, but also at a regional basis as well, and also for livestock and also for crops. And just to give you one of the figures that we came up with, you can see here at the top we have the different handles here, and this is the greenhouse gas emissions from land use change, greenhouse gas emissions from soil, greenhouse gas emissions from energy, and whether that energy is where that energy comes from. And we can look at a historical trend since the 1970s. And if we look at the emissions here per energy per produced unit of food, because what this allows you to do is to look at the emissions per unit product, but also the emissions per unit area. And you can see the greenhouse gas emissions in total have increased somewhat. But what's really increased was the greenhouse gas emissions associated with energy use in agriculture. In fact, some of these figures, some of these lines are going below 1, which is what we set at 1970. And so greenhouse gas emissions, land use change per produced unit has actually been falling over time. So what I really liked about this kind of analysis is it did allow you to look at regional differences, it allowed you to look at a global picture, it allowed you to look at livestock, it allows you to look at crop production as well. And there are reasons why this is possible. It's because in mathematical terms, we're dealing with an identity here, we're not actually dealing with an equation, but that's another discussion. What we have also thought about is how we can perhaps link these different identities so that we can look at some interactions between diet demand and diet supply. And the red arrows are showing where in the different identities, for instance, the Kaya identity, that this also appears in the Kaya Porter identity, population appears in this Kaya identity and in the diet demand. So I think we haven't actually done this work, but I think it would be very interesting to do this work in that you could then look at how you could connect wealth, population, consumption, and greenhouse gas emissions in a single analytical framework. Sorry, I'm going down. So that was the first of the two methods I wanted to show you. And the papers have been published in Global Change Biology and Global Environmental Change, if you're interested, and also the European Journal of Agronomy. The second way in which you could perhaps look at the human food system, and this is really taking the work of H.T. and Eugene Odom. They were at the University of Florida in the United States. And they developed an idea that what you could describe these systems as is the amount of embodied energy in them, what they call emergy. And this means that you can then start off with how much sun, how much radiation comes in from the sun, how much of it is used in producers, how much of it is used in primary consumers, how much is used in secondary consumers and tertiary consumers, and how much the energy actually increases as you go down the scale here. And this allows you, this kind of analysis, I haven't got time to go into any more details about it, but if you're interested, you should be looking at the work of H.T. and Eugene Odom. It does allow you to come up with some quite interesting indices. This is from an experiment that we did at Copenhagen when we had a combined food and energy system, which is an agricultural system that I put together in the mid-90s, which I wanted to make completely carbon neutral. We did it in 1995, I think. And we compared these indices with a conventional wheat field. So for example, if we look at the percent of renewable energy used in these wheat and also in the combined food and energy system, you can see that in the CFE system, then 30% of the energy we're using is actually renewable energy. We're only about 5% is in the wheat system. And you have these environmental loading ratios and these environmental energy footprint ratios. So it does allow you to look at other aspects of cropping systems and food production systems, which are not just based on input and output. There are other indices which are perhaps more relevant from an environmental point of view. And again, this is a very rich field, I think, for people to perhaps look at in the future. And the big question here in the end, and one of the things that I worked on last year in Montpellier with a group of people at the University of Montpellier, the Advanced Research Institute at Montpellier, was what does it mean for these indices and these ways of producing food if you have a circular food system or if you have a linear food system. You can see here, if we take it on the right-hand side, with expected production maybe of 100%, that by the time we get actually down to the consumption, then we've lost about half of that. And that some of it will, of course, be as waste, it will be as emissions, it will be as pests and diseases. But what does this mean if we try and make this food system a circular food system instead of having a linear food system? That's a question I would be very interested to hear your comments on. So this, to just draw this part of the talk to an end, I think a lot of the science that you hear in food systems and food production is that we need to produce more from less. I think we've developed the science of producing more, consuming more, and wasting more. But I think for the 21st century, we have to say, what does the science of saving more, consuming enough, and wasting less look like? If you were going to set up a research program which had those as the goals, what is saving more, consuming enough, and wasting less? What does that actually look like? If you improve the efficiency of production, it does give you more from less, but it still increases emissions. That's what you could see definitely from the from the stuff I showed you, the graph I showed you from the emissions, global emissions from crop production. It does improve, it gives you more from less, but it still increases absolute emissions. Improving efficiency and limiting consumption, that means getting rid of things like waste, gives you enough from less and also limits emissions. So what does a food and economic system look like for enough from less and not more from less? Enough from less is now one of my mantras, in fact. Excuse me. So the conclusions from this section are that we can use simulation modeling and detailed analysis and lots of experiments to look at the emissions from agricultural systems, and we've done that for about 40 years. We can try and look at identities. We can try and look at Kai identity and the Kai Porter identity, for example, and also to finally, in an area which has been much less used, is to think about using emergy, the embodied energy, because that does provide you with a common energy currency. And of course, when you are dealing with these different methods, then you need to have a balance between accuracy and precision, simplicity and complexity, energy quality and quantity, and urban and rural. I mean, there are many different balances that you maybe can look at using these different methods. And I think it's really important to start building the capacity in how to regenerate models. The problem with modeling is now that most of the modelers are at least as old as I am, maybe even older, and we need a really new generation of people who understand what modeling is and how to do it. So I want to move on now. I don't know quite how long I've taken in that part of the talk, but hopefully I've only taken about half of it. I now want to move on to a discussion really about science and the norms of science, because I think it's important that PhD students and postdocs and also practicing scientists have at least thought about what is science and what are the norms of science, because science is a human activity, therefore it has societal norms. I just think it's interesting to look at these. And I hope Hazel has sent out a chapter that Bernd Wollenweber and I, Bernd Wollenweber is a colleague here in Copenhagen, we wrote in, it was published by the European Academy of Sciences, called Progress in Science, Progress in Society. And we wrote a short chapter in that book, and I think it's hopefully been sent out to the people who are listening to this talk. And the title of our chapter was actually Science in an Age of Unreason. I mean, science, of course, the great breakthroughs in science happened, you know, the triumph of reason over mystery, and happened, of course, in the Renaissance and also later. But the feeling is that we are perhaps moving into an age of unreason. So, what is science? What are the ethos? What is the ethos and norms of science? How is perhaps research cultures changing? And is there a way out of this? Is there a way that we can think about science in the age of unreason? This is a rather traditional view of science. It's about established knowledge, which has been systematized in reference to this discovery of general truths, accepting the fact that what is a truth can change over time. And a classic example of that would be the change from Newtonian physics to relative physics, to the physics of Isaac Newton, to the physics of Albert Einstein. Isaac Newton's physics worked fine as long as you're not too close to the speed of light. And when you are close to the speed of light, you have to revise your knowledge and revise your hypotheses. And science is also a process of observation, experimental investigation, and theoretical explanation of phenomena. So science is also a way of pursuing knowledge, and it's not only the knowledge that pursuit of knowledge actually produces of itself. So science is organized, knowledge is specialized. It can be based on experimental evidence from expert studies. It tries to establish authority by having organized institutions like academies of science, for example. It tries to be rational, it tries to be evidence-based and communicated unambiguously. And it's reliable, it's based on reason. And I think actually there are a number of parallels between science and what we consider the law. If you are involved in a trial you maybe have committed an offense and you're involved in a trial, then there are certain processes that are also gone through which are rather similar to what we have as the parameters of science. So, for example, if evidence to produced for a legal proceeding has to come perhaps from numbers of different sources. You could not have just one piece of evidence which would convict someone. You have so it has to be evidence-based, and I think that evidence has to be communicated ambiguously. You have well-organized institutions which have history in dealing with people. So, the legal system is based on precedent, and it's also based on principles. And there are a number of different ways in which science and law, I think, are very, very close to each other. And in fact, we talk about scientific laws. I mean, we think about scientific laws and how they've been established. So I think there is a great link between what we regard as science and what we can think of as law. And research cultures differ. So different societies have different political agendas for science. Often traditional societies don't have any organized social activity for the production of knowledge. Their production of knowledge is very much based on experience and tradition and storytelling, and how things are passed down from generation to generation. It's very indigenous knowledge. You can have theocratic societies where the role of science is to sustain the authority of religious beliefs. And of course, that happened in Europe in the Middle Ages, where the question was, is the Earth the center of the universe or the center of the solar system, or was the sun the center of the solar system? And there were people who were made to feel very uncomfortable because they held the view that the sun was the center of the solar system. In totalitarian societies, scientific activity is incorporated into the state's ideology. The absolute classic, there have been many examples, but the absolute classic example of this was in Soviet Russia, Soviet Union in the 1930s, particularly in their agricultural policy, which was based on Marxism. So they said, all you have to do is to move spring wheats into a cold environment, and they will turn into winter wheats, because everything is controlled by the environment, and that's what Marxism says. And of course, this was Lysenkoism. This was Lysenko, yeah. And he basically was one of the reasons why there were massive famines in the Soviet Union in the 1930s. And then you have technocratic societies. Scientific research is linked to technological innovation, and in many industrialized countries, that's actually what's happening now, undertaken by companies and organizations seeking economic profits. So research cultures are not fixed. They depend a lot on which society the research is ongoing. And research cultures are changing as well in terms of pure basic curiosity-driven research at universities, which is usually evaluated by peers. So you submit papers to journals and they're evaluated by your peers. You can have post-academic or post-normal science, where it's more mission-orientated research, which you see in governmental labs, and the product is usually evaluated by the users of the research. And then applied, you can have it research within industry, where industry is regarded as the client for science, and this is defined and evaluated by clients. And then technoscience, which is the merger of scientific with technological disciplines, research and development. And this is, again, this is research towards specific aims. And if you look at, for example, now, the Horizon 2020 program in Europe, that's very, very heavily applied. It's very much techno-science. It's to solve problems for industry. And I think it's actually having the effect of turning many universities into consultancy businesses. I mean, that's what they've become. They're not rewarded now for just the generation of knowledge. They're rewarded for doing consultancies for a lot of private organizations. But this has not always been the case. And I want to now start to discuss the work of a man called Robert Merton, who was an American sociologist in the 1930s. And he came up with a certain number of norms that he thought were relevant to scientists and what defined science. And I just wanted to present these to you now. So his first norm was communality. A scientist ought to make knowledge accessible to other scientists as knowledge is common ownership. It was universalism. So scientists ought to assess knowledge claims not based on pre-established, but not to assess claims based on pre-established interpersonal criteria, i.e. not depending on race, nationality, or religion. Scientists are supposed to be disinterested. They're meant to be able to hold back and look at their work from a somewhat of a distance, and also to not hold or to at least declare any conflict of interest they can have, which may corrupt the research results. It's in this sense, I think scientists may be behaving as journalists. You know, we expect journalists, when we read a good newspaper, we expect journalists to present in as disinterested a manner as possible the news. There can be, of course, opinion and discussion, but we do expect our journalists to abide by a disinterestedness criterion. And then the final one for the word kudos is organized skepticism. Scientists ought to conduct organized quality control of their research results. So there should always be a skepticism attached to the work that's been done. And that in a sense is how science progresses. If we all went around and said, oh yes, that's the problem solved, and anybody wasn't asking questions, then you can see that is not example of organized skepticism. And I just want to tell you a personal story now. One of the things which is very important, I think, was very important for me becoming a scientist was this chap here. This was John Harper, who was my PhD student. He was the father, if you like, of plant population biology. And he also was one of the co-authors on the main ecology textbook, Bacon, Harper, and Townsend. And he inspired me. I mean, it's the only way I can talk. He was the most intelligent person I'd ever met in my life until then. And I loved discussing with him. We had many, many arguments. But he was a mentor and he was a leader for me. I mean, he wasn't a manager, he was a leader for me. And some of the, what are the characteristics we look for in a scientific leader? We have many scientific managers these days, but I think we lack sometimes the scientific leaders. And John Harper was definitely my scientific leader. So the norms of science, I'm going now back to the Mertonian norms of science. The norms of science have changed. So communality has given way, I think, to a certain amount of solitariness, solitary work. So instead of rushing out to publish your research results, I mean, it's actually part of the law here in Denmark, that if you find something which is patentable, your first task should be to secure a patent for it. You can actually be prosecuted if you don't do that. So this is going a long way away from the communality of science. And I do go back, I mean, Linny would know about this at working in the CG system, that the way that the CIMMYT and these organizations in the CGIA system operated when they were founded in the 1960s and 1970s was based on complete openness. When Swaminathan went to visit Norman Borlaug at CIMMYT and asked him for his wheat varieties, his rust-resistant wheat varieties, Borlaug just opened the cupboard and said, "Take whatever you want." And that was very much communality, and it's, I'm afraid, given way to solitariness. Universalism has given away, I think, to particularism. The scientists are often continually reminded that their work has been sponsored, and this is what society is expecting to get back from them. So it becomes a system of problem solving rather than a system of knowledge creation. Disinterestedness has definitely moved over to interestedness. What governs the work that many scientists do these days is what are the funding opportunities, and this is particularly the case when you have a success rate of maybe 6% of one in 10 research applications get funded. I mean, there's no other activity that humans do. It would never happen in business, for example, that you only got 1 out of 10. This is an enormous waste of time for scientists. And as a result, science is becoming very much performative. We look at, the first thing one looks at is what is someone's H index, how many papers have they published, how many citations have they had, as if this was some kind of indication of quality. And this is also very much the case that if you have a science area which is very heavily funded, then of course the number of citations in the H indices will be higher. There's ways in which skepticism has given way to dogmatism, in that if you have a particular theory that you want to preserve and use to perhaps get funding, this is given away to organized dogmatism instead of having some skepticism about the work that you personally have done. And so what do we need in the future? I think one of the things that Bernd Wollenweber and I came up with was a need for a new enlightenment. And I think we have to have scientists, we have to maintain our confidence in the process that in which we're engaged. So the power of scientific reasoning is the ability to accurately make predictions based on systematically acquired evidence. I think we should always remember that. And this is very much, if we think of what's happening now with the coronavirus, the relationship between science and politics here, what has science done? It's interesting, I think, that science to begin with in this process has had a very, very very important role. And what has happened lately, I've been thinking particularly the United Kingdom here, is that the politics has taken over from the science. And I think and there has been an underpinning of or a diminution of the confidence that scientists have used in dealing with COVID-19. We need a better dialogue between science and society, which has to accept that science provides reasonable evidence-based facts and not fake news. We have to think of the threats to the objectivity science. These have to be acknowledged and dealt with. IPCC had problems with this a few years ago, but of course that was also part of a scheme by climate deniers to try and undermine. I mean, that's happened before. It's happened when the debate about smoking and cancer came around in the 1950s and 60s. So there will be deniers who will always try to underpin the objectivity of science, and these have to be acknowledged and dealt with. And again, conviction. Science has to identify evident denialism and pseudoscientific claims. So my conclusions really, if I try and put together both parts of the talk I've given this evening, I think there are several ways to estimate greenhouse gases from food production and food systems. And I think it's, of course, again, very important that we have a variety of methods, because that adds robustness. If all the methods are pointing in the same direction, that adds robustness. This is one of the things that we have to deal with in the IPCC, that we try to look for different pieces of evidence to see if they were all pointing in the same direction. I think it's important to know emissions per unit area, per unit product, and link emissions to diet, population, and wealth. And I think, hopefully I've shown you a way in which that can happen. There is a lot of interest these days in thinking about linear and circular food systems. Can we move from more from less to enough from less? I hope that as young scientists, you at least have a good think about what you understand by the norms, the kudos of science, because it's important for all scientists to know, and you need to take a position on this. You cannot be a scientist, I think, really, until you've taken a position on what you consider to be the norms of the job you're doing with it. In a sense, scientists, not quite the same as doctors who take a Hippocratic oath when they become doctors, but I think scientists, and there have been papers in Nature, for example, about it, that as a scientist, you should be taking an equivalent of a Hippocratic oath to defend your position. And I think that science definitely needs more leaders than managers. We have so many managers these days. I'm very fortunate that I don't have to have any manager. I'm my own manager these days, or I'm managed by someone else. But we definitely need more people who are going to inspire young people as leaders than managers. I'm afraid the tendency is to go the other way. So, whoops. Sorry, I'm going down. Yeah, my final slide is just to say thank you to a number of groups and people, that my previous climate and food security group at Copenhagen University, the IPCC, and the work that the special report, the land use for climate change authors, Cynthia and Tim Benton and a number of other colleagues. They did a fabulous report, I think. Chinese Agriculture University, they helped with some of the data and some of the analysis we did. The Australian National University and Tokyo University colleagues, they helped with the work we did on the 3 capital cities, and the University of Montpellier colleagues. That was a wonderful time to spend in Montpellier thinking about linear and circular food systems. So I hope I haven't gone too long over my time, and I'm happy to take any comments or any questions. Thank you.
Thank you, John. I'm giving the applause on behalf of the audience, our 50 or so participants. We have a number of questions, and I'll just dive in and give you a chance to start responding.
Right.
So,
okay.
First one, Titus. Yeah.
How long did I talk for? Was it over time?
We have now about 35 minutes.
Okay, so it's a bit longer than.
Plenty of time.
Okay, good.
Thank you. All right. So from Titus Abdini, Titus asks, moving towards circular food systems until today, we don't have a firm approach to assess these circular food systems. Do you think the 2 approaches you mentioned in the first phase of your presentation can be applied to assess the circular food systems? And then I'll mention the other questions. Titus also has a small note about, can you explain more about CFE and why did you compare it to wheat systems? Then from Glory Edwards, she asks, basically that food waste seems to be a solution for ensuring food security and sustainability. However, not necessarily more production or intensification, but many developing countries are still focusing on production and not on managing waste and loss. Can you comment on this, please, and give any examples of countries that have navigated this? How can we shift from production to reducing food loss and waste and also get enough for less.
Okay.
Let's take those first three. Thank you.
Okay. The first question, you have to just say what the first question was again. I've forgotten now. So
No problem. Basically about moving toward.
Oh yeah. Okay. Moving towards circular. Yeah. Thank you. Well, yes, I think you could use either of those two methods to look at circular and linear food systems. I think it would be very, very interesting to do that. Yeah, you could both use the identity approach and also to look at, I mean, the odor emergy approach could also be used, I think, it would be very interesting. In fact, a few years ago, I had a master's student who used the emergy approach to look at this combined food and energy system. I'll tell you a little bit about that now. When I went to Copenhagen, the Research Council gave me quite a lot of money, not in my back pocket, but so I could do some research. And I said I wanted to set up a system which was a food production system which was fossil fuel neutral. And so we set up a system where we had belts of fast growing trees, willows and poplars and other species as well, some nitrogen fixes in there as well. And between these belts, we had organic food crops. So we had food and fodder crops. So basically what happened every 4 or 5 years, you cut down the trees, you send it off to a combined heat and power system, and that produces electricity. And when we did the energy analysis, I mean, even when we were producing the food, then that does consume some fossil energy. But we were able to produce at least many times more. I think the fact was about 5 or 6 times as more energy from the biomass belts as we were using in the production of food components of the system. And the biomass belts were about 10% of the total area. So we were able to produce a fossil fuel energy neutral system, what people would now call net carbon zero, net emission zero, from this system. And I had a PhD student, or no, master's student, many years ago, who did an analysis of the CFE system based on the emergy methodology, and so we did an analysis of that. Linny, you have to then tell me about the intent. What was the question about intensity? About the intensification? About waste. Yeah.
Yes.
Okay.
And especially examples of countries that are making that transition in developing country context.
In developing country context, I cannot think of any off the top of my head. Maybe you can. I don't see that. I can think of places in the developed world where this is starting to happen. I see here in Denmark and also in Sweden that people are taking much more notice of waste. I mean, all our food from our house is sent off, is recycled. We separate our waste product, our waste food, and that's taken off and made into compost, I think. So in developing world, but one thing you have to bear in mind very much so is that most of the cereals that are produced these days and soybeans is actually fed to animals. So this is why it's not about having more from less, but I think it's about having enough from less. I'm not a person who says you should never eat meat. I think it's very important to have dairy products and milk and cheese and these things. It's a very important protein sources for children. And my daughter's second baby, I mean, she wouldn't survive without dairy products. And so I think, but the point I was trying to make was that it's about changing the paradigm of research, really, away from producing more, consuming more, and wasting more. What does the science paradigm, an agricultural science paradigm, look like, which has as its mantra enough from less and not more from less?
Okay, thank you. John, would you prefer I go through the questions one by one, or would you rather take
Yes,
cluster?
just one by one, because my memory, I can't remember that.
No problem. I'm
Okay.
going to jump around just a bit because we have a number on circularity, and I want to get
Yeah.
some other topics in here. But
Okay.
inspiring talk, thanks. This is from Florencia Garcia. One of my concerns is that a hidden aspect of this career is to get high impact research. I'm sorry. One of my concerns is that a hidden aspect of this career to get high impact research is that there, even in the research field, there is a definition of developed and underdevelopment, which makes developing countries take research priorities that respond to the edge of knowledge defined for some parts of the globe that are not necessarily responding to local needs. So I think basically that the edge of knowledge in this field is being defined by the North rather than necessarily developing countries or local needs. Could you comment on that?
Yes, I think that's generally been the case, and one of the things as you kindly mentioned, Linny, I've been made the editor-in-chief of Frontiers in Agronomy, and one of the things that actually attracted me to that position was the fact that it was going to be open source. So I think open source publishing is a way in which you can localize, you can make things more local, you can make research more local. And then, because what you're doing is you're getting out of the control of the publishing houses and companies. When I was editor of the European Journal of Agronomy, this was run by Elsevier. And when we started off with Elsevier, when I started off with him in 2007 or something, they were very interested in the science, but by the time I finished with them in 2016, they were just interested in making money. So I think that open source publishing is a way in which we can move away from the idea of developed countries setting the research agenda, and it opens up more possibilities for scientists in developing countries to have an opportunity to publish. And I think what's happening is will be that when you have an open source and you pay a certain amount of money to publish an article, that doesn't mean it doesn't get reviewed. It gets very heavily reviewed. But it will be cheaper. It'll be cheaper for developing countries to go through that process.
Thank you.
I hope it answers your question.
And from Marcelo Beltran, thank you for the interesting presentation. I want to know, just jumped away from me. I want to know if the no-tillage system is an important practice which could reduce the energy use in agriculture because of the higher impact of energy that you showed on your graph.
No tillage, well, no tillage is a bit of a two-edged sword in some ways. I mean, of course, if you're not turning over the soil, then you're not, you're cutting down the emissions. But I think you have to bear in mind that no tillage often does mean you have to use herbicides. I mean, in conservation agriculture, I mean, you can't get away from the fact that you have weeds, and then the energy used, if you try and do this mechanically, if you try and do the weed control mechanically, this can lead to a large use of fuel. And I think the other thing about trying to think about how you can store carbon in the soil, I mean, this 4 per thousand initiative that the French have gone in for, is that it does change the paradigm of agriculture, because it means that you have to be much more involved, much more interested in perennial crops than annual crops. So it does change very much how you would, what kind of agricultural systems, because, okay, I mean, you can have practices which allow you to put carbon into the soil, but you got to keep it there. And the sooner, if you keep it in the soil and then you start plowing again, then you're going to lose a lot. So you have to be, I don't think it's I'm generally in favor of agriculture becoming more perennial. In fact, I've had many discussions with people at CIMMYT about why don't they make perennial wheat? And they laugh at me when I do that. They say perennial wheat's a joke. So, well, fair enough. We'll take this discussion. But yes, but I think that you could do some really nice work and some really nice calculations of looking at the whole look at low tillage in the context of a food system. Again, please get away from this idea that we solve agriculture's problems just by dealing with production. We don't. We have to think of this in the context of a food system, as they did in the special report for land use and climate change.
Thank you. And a question from Hazel. John mentioned in his slide with the equations connecting wealth, population, consumption, and greenhouse gas emissions based on the Kaya identity, that further work needs to be done to develop these. I'm interested in an example of how these equations could be applied, and what would further research involve?
What we did when we did the Kaya identity, the Kaya Porter identity papers, was first thing we did a national analysis. We took Denmark and we applied those identities. They're actually not mathematical equations to be perfectly accurate. They're actually mathematical identities. But we took Denmark as an example. Then we that was published in European Journal of Agronomy. And then we did the global analysis, which was the trends of emissions over the last 40 years. That was in global change biology. And then we did a regional analysis. We broke down the global figures into a regional analysis and did that. Again, that was published in Global Environmental Change. I think it would be I don't know anybody who's tried to link these things together. I haven't had a chance to do. I don't have any PhD students anymore as a retired professor. And but I think it would be extremely interesting to try and look at those and see how they interact with each other. What was the second part of that question? Sorry, I've missed that. What was the second part of the question?
What would further research involve?
Well, I think what further research involved would be some kind of case studies. I mean, it would be very interesting to take this to do this kind of analysis in a very, highly developed social, like here in the Scandinavian countries and maybe in the US and then in other countries as well, to look at the differences, I think, between different types of, what are the trade-offs? I think it would be absolutely fascinating, actually.
Okay.
So I think something which is national, regional, and with different examples from different parts of the world.
Okay. I'm just going to encourage the group to keep asking questions. I'm now cycling back on some of the same people who asked questions before, so I apologize for that. But they're great questions. So keep them coming in, please. This is from Glory Edwards, concerning that science progresses, I'm just going to reword this a bit. Concerning that science progress aligns with societal progress, increasingly participatory modeling is becoming a norm for complex social ecological systems analysis. But how do we increase the credibility for these participatory methods? Have you carried out such participatory modeling processes? How else can we increase the social impact of our research?
I haven't been involved in that process. I mean, I think, again, I think it's about being robust. I don't think you should just use one method. I mean, I think if you use a different, 2 or 3 different methods and they were all pointing in the same direction, then I think that you have some more confidence. But I don't think you can just take one method and say, this is going to you have to examine a number of different methods, I think. and participatory, that kind of citizen science participatory research is one approach, but you have to look at other ones as well, I think, and hopefully they'll. And you know, there's two things really. One is about the robustness, and the robustness is about using different methods and seeing whether they point in the same direction. And then you can also look at the amount of agreement. So you can have the robustness, and then what is the degree of agreement between these different methods. So having a variety of methods is very useful, I think, and very. Yeah, sorry. I've just noticed something behind you, Linny, that I want to ask you about. This post you have here, Stemlungen. This is Norwegian, right?
Actually, it's from Berlin. It's the lake where my mother grew up. Yeah.
Oh, okay.
But it may have some affinity.
Looks a bit Scandinavian. Yeah.
Yeah. Okay.
Sorry.
No problem. You're the first person to ever ask about it. A question from Ngoni, one of your PhD students, and one of my great colleagues. Thank you for the excellent presentation. What lessons can science take from the COVID-19 crisis? Well, this is an evolving crisis. Do you think science will benefit from the crisis?
Ngoni, that's yeah. It's a very good example of the relationship between science and society, and it's interesting. I think that I mean, in the UK, you know, after 2016, when they had the Brexit, you know, the UK becoming independent of the European Union. I mean, politicians were going around saying, we don't need experts anymore. We don't need science anymore. You know, people just have to do what they're, and you saw it in the States with Bannon. I mean, you had to be authentic, which basically meant you just did what your gut feeling was. And then, you know, then you come into this car crash of COVID-19, and suddenly scientists are flavor of the moment. And I hope, but the thing is, again, that science had a good start with COVID-19, I think. I mean, it was very well, you know, you had these people giving their views about how things were going to develop, and then I'm afraid I think it's moved. COVID-19 has moved away from being a discussion on science to being a political discussion now, and so scientists are being used as a kind of fig leaf, if you like, for politicians. They will agree with the scientists when the politician thinks it's in their interest, and if it isn't, then they'll ignore them. But to answer your question, Ngoni, I think this can only add to the reputation of science. That, you know, the people who are going to save this situation are going to be the people who are either developing the vaccine or have been developing the models. That's been very, very important, I think. And I just hope that people don't forget it, really.
Okay. Another question from Florencia Garcia about circularity. I wonder if the options, whether it's circular or linear, are not both themselves an important reduction. Wouldn't it be possible to imagine a process where you have different lines and circles, you know, some close in on themselves, others interconnect, so that we can combine both of these and not have one or the other? Sorry, Florencia, yeah. I ad-libbed a bit. Yeah.
Yes, of course. I mean, I'm only trying to show the extremes. You know, of course, and it's also a question of the scale in which the spatial scale at which you could do design these particular systems. You know, there were just illustrations of the, if you like, the outer limits of, you know, moving away from a strictly linear. I mean, I think a strictly linear system intrinsically produces more waste. It's a more wasteful process. To keep the system running, you've just got to add more in at the top, and more will come out at the bottom. And it's a different again, it's a different socioeconomic paradigm as well, I think.
Thank you.
But they're extremes. Yeah.
I have a question. You know, we've talked quite a bit about framing and also the limits of certain frameworks of analysis. And I'm thinking about the IPCC inventory accounting system and how when we talk about agriculture and agricultural emissions, you know, we're not reflecting, one, the kinds of drivers that you show in the Kaya Porter identity. So it's not really giving us a sense of why these emissions are occurring where they are, especially when we think about trade and consumption happening in some countries, but food is being produced elsewhere. And two, it makes it very difficult to talk about the scope of the system. You know, agriculture is not defined in the IPCC, but also, you know, we've got companies dealing with life cycle analysis, and we've got people talking about fertilizer emissions, and, you know, we've been talking here about waste, and there's so many different ways to cut this pie. So I guess my question for you is, if you could do an IPCC special report to talk about how to account for agriculture and food systems in a way that allows us to reduce emissions, to really understand how to reduce emissions, what would you recommend for that accounting system? What would be the report? What should that report be about?
Well, I think it has to be, what we tried to do in two things about the KPI. One is that it does allow you to link emissions to agricultural practices. And also, if you take it on the food system, to things that people actually do. And the second thing is that it's because it's not a mathematical equation, it's a mathematical identity, it's scale independent. You can use the same handles at different scales, because all you're doing is moving these handles up and down, and that allows you to be scale independent. So it does allow you to, as we did, look at national level, regional level, and global level, using the same method of analysis. And so I think that's where I would be trying to link agricultural processes to agricultural emissions. I don't know whether that is anywhere near an adequate answer, but that's off the top of my head what I would think. Yeah,
thank you. No, it could be the topic of a long conversation. Thanks.
Yes.
All right, a question from Titis Abdini. You presented the example of food systems in different capital regions. Is the boundary only for environmental and economic assessment? When we want to reshape our food systems, for example, to make them more resilient in response to the pandemic crisis, how do you suggest we should draw our system boundary?
Well, the answer to the first question was, yes, we did choose the socio-economic boundaries of the capital city. So these were, you know, what is the capital city plus the hinterland around it? What is the greater Tokyo region, for example? So that was taken as a geographical or socio-economic limit. Sorry, what was the second part of the question, Linny? I didn't remember the second part.
If you have the goal of reshaping your food system to make it more resilient, what would be the best way to define?
How do you draw the boundaries of that?
Especially in relation to the pandemic.
Oh boy, that's
challenging questions.
That's putting two things together at the same. That's trying to put two things together at the same time. I don't really have an answer. I can't really think of an answer. The only thing I can think of is how, in a sort of slightly parallel situation, was how foot and mouth was dealt with in the UK when they had that foot and mouth outbreak in 4 or 5 years ago now it was, but there was a very bad outbreak of foot and mouth. And there the boundaries were basically designed, the boundaries for the process, for the culling that went on was basically designed. It was called this contiguous cull process. So that if you, I'm not recommending this for COVID-19 at all, but what they did with the cattle was that if there was one animal in the herd which was infected, then the whole herd got slaughtered. And so, how do you do this with COVID-19? What does that tell you for COVID-19 in the food systems? I think what it means is that the food systems would become more localized. I think, I mean, you would be, if people are socially distancing, if people are required to be socially distancing, then I think where you get your food from and how you get your food and what you do with it, I think becomes a more local issue. But I don't know whether that's just nonsense or not. It may just be nonsense. Good. I don't actually have a really good answer to that. I'm sorry.
It's a tough one. Yeah, it's a tough one. And then another question from Titus. Can you explain more about CFE? Why do you compare it to wheat systems?
Oh, that was the first question. That was the first question you asked.
Yeah, I thought, I know that I asked it. I wasn't sure if you addressed it. So Hazel, I think we can. Yes, thank you. Good. And also the question from Glory Edwards about circularity has been answered.
Yeah.
From Stephen or Stefan van der Westhuizen, I'm sorry for mispronouncing your name. This is not really a question, but maybe more of a comment. He read a paper today about the use of p-values and looking for the less than 5%. And how it may lead to increased false positives in poor science, just to have more publications. If journals would start to incorporate more elaborate ways of assessing data and models, we would start to move in a towards more Mertonian norms of science. Could you comment on that?
Well, yes, yes. I think a negative result in science is as important as a positive result. I mean, that's one thing that I think is. I mean, I can remember the discussions many years ago about coal fusion. I mean, this was going to be the thing which was going to save the global energy, and people looked at it, and then in the end they decided that you couldn't actually have coal fusion. So that was a very important result. It was a negative result. It became that paper by Pons and someone else who did the work on coal fusion became the most cited paper in Nature that year. So producing negative results where you have insignificant p-values doesn't necessarily mean that you don't get a good paper. A good paper can be, I mean, if you can write a paper in theoretical physics, you don't have any p-values in theoretical physics. It's just ideas written in mathematical equations. So I don't think that there's always a link between the use of p-values in a journal and how well cited that paper becomes. I don't think that's the case at all. In fact, the paper I've had most cited doesn't have a p-value anywhere near it, I don't think.
And the final question from Sebastian Cambareri. I'm not sure I got that right. Sorry.
Yeah.
In the second part of your presentation, you mentioned ethos. How would you define ethos for science? And also, is there a PhD ethos? Great question.
Great question. Ethos, I mean, ethos is what do we recognize as scientists to be the general characteristics of what we do? What is we know, we can understand. I mean, for example, plagiarism. If you copy someone else's results, and publish that as your own. That's very much against the ethos of science. The ethos of science is that if you have a discussion with someone about some work you're doing, then they respect that, you know, you may be the originator of that particular idea or piece of work. And the ethos is that you don't copy that. Some people try to do it, and when I was editor-in-chief of the European Journal of Agronomy, I once had a paper sent to me from a country I won't mention, where there was 75% of the paper was completely copied from other papers. This was the highest plagiarism I saw in the time I was editor-in-chief of the European Journal of Agronomy. That is completely against the ethos of science. And the ethos of a PhD, well, I think it's much harder these days, but even with Ngoni, when he was a PhD student, and the excellent PhD student he was, hopefully the ethos of the PhD was that you did a PhD because you found something really, really fascinating and interesting. I can't think of really another better reason for doing your PhD than having this idea that doing a PhD is a difficult process. It can be a very, very lonely process. But I think that the ethos of doing a PhD is that you have to find something that you think is interesting and more than interesting, you think is absolutely, you know, worth getting up in the morning for. And you know, if you're in a pub and you're going to talk to someone, you've got 2 minutes to explain what your PhD is about. That's when you really find out whether you're interested in the PhD. You know, if you can explain what you're going to do in that very, very short period of time. So that's for me, the ethos of a PhD is, and it's what I learned from John Harper. I mean, and you get an ethos of a PhD, I think, by interacting with very, very interesting and provocative and argumentative people and sorting your own ideas out. I think that's also very important.
Wonderful. So we're coming to a close.
Okay,
wonderful.
Thank you. Thank you to everybody for the questions.
Yeah, fantastic. We did have a comment about how students might be able to get in touch with you. I'll let Hazel address that offline. We don't have to address it right now. And I just want to say, again, on behalf of the GRA and CCAFs, thank you so much, John. It's wonderful to impart your wisdom. Applause to you. Yes. And to
everybody.
Yeah, to thank the participants for their great questions, and to remind people that the upcoming 2 sessions are quite important. The next one will be a thematic student session on rice systems presented by Ole Zander from Erie. And I can say, as one of his colleagues, they've done probably more work than anybody else on the CGIAR in advancing certainly alternate wetting and drying in rice and thinking about monitoring of those systems. And Ole is a great speaker. And then a special session which I find fascinating, on farmers' perspectives, with a panel of young farmers from the World Farmer Organization Gymnasium. So thank you to everybody. Thank you to Hazel for organizing this, and to Sadie for, I don't know what you do exactly, Sadie, but recording this, and to Rebecca as well. Yeah. Thank you.
Thank you.
John, thanks everyone.
Yeah.
Bye-bye.
Thanks.
Bye-bye. Bye.